talk to us about some lessons he learned from compiling Linux with Clang LLVM.
Great, thank you. Yeah, so I had the pleasure of giving this talk actually last week at the Linux Collaboration Summit. So I got feedback from the Linux community. They seemed very excited about the idea of being able to use Clang and LLVM and a lot of the benefits it brings. So I don't need to convince this group of the benefits of it. What I would like to do, though, is get feedback from if there's anything I'm missing from my presentation that you think would be a benefit to the Linux community, please tell me, because I would like to make my pitch even better. Also, I will present many things which I came across which I just don't understand. And so they are issues, but I would definitely like your help to try to identify what the cause of them is, and then I can take the action item of going about it and fixing it. So overview, I will talk about cross-compiling with ARM and my experience with it, because I'm not just compiling the kernel, but I'm also generating a rootfs using Clang. And then the part of just building the kernel with Clang, and then actually how far I've gotten running the kernel that was generated with Clang, and a brief to-do list, which is definitely incomplete. So why would I want to use Clang to compile Linux? Obviously, it's grown up using GCC. You know, what is the pitch to the Linux community that would make them want to do this? And for QuIC, what is our interest? So for QuIC, Qualcomm has a system on a chip, and as many other SoC vendors have multiple different cores in it. We have DSPs in there, we have CPUs, the GPU, and so ideally we want a single system compiler for all these different targets that we can use, and we want to optimize that. So for us, having disparate tools is really more difficult to scale. And our idea really going forward is we want to make Clang and LLVM our tool set of choice. So obviously better diagnostics. I won't spend too much time on this. People are familiar with this part of it. But being able to identify which things are GCC extensions is very beneficial for the kernel, because I think a lot of developers aren't even aware of how many GCC extensions are actually used by the kernel today. And Google takes advantage of this to the point where they build all the things, even if they're not releasing it with the Clang build, just to get this diagnostic output. The fix-it hints, again, were a useful feature. I think that the people using GCC aren't just used to having this kind of debug output. Macro expansion, definitely a nice feature because there's a lot of macros in the kernel. And this was from the BlueZ project. So BlueZ developers used the static analysis tool from Clang, ran it over their whole code base, generated the static HTML files. So they found some useful things as they're going through it. So you can see the Linux community is starting to use Clang more and more. Certainly, at least for the diagnostic output, the kernel just hasn't been addressed too much in the context of Clang. But it is being more and more used by open source projects. So Minix recently announced that they have moved to Clang as their default compiler. FreeBSD has been working on compiling the whole FreeBSD distribution with Clang. And they also use Kali for test generation, which is built on top of LLVM. In Android, LLVM is a key part, obviously, of RenderScript. And it's supported on multiple architectures. And then in the standard GNU Linux world, LLVM is still a hard dependency today for the graphics stack for Gallium 3D. There's an LLVM pipe driver, which is used if you don't have a GPU, and they can simulate the instructions in the CPU. The CL state tracker uses it, and they're even looking at it for optimizing the GL shader. Recently, a Debian developer tried to use Clang to compile the whole world of Debian to see how far he could get. And this is actually the second attempt. It's Sylvestre Ledru. And he had a lot of glowing review of Clang and how far it has come. Some of the quotes were, from a community that's very used to using GCC. I thought this was very telling. My personal opinion is that Clang is now stable enough to rebuild most of the packages of the Debian archive. In a few years, coupled with better static analysis tools, Clang might replace GCC and G++ as the compiler used in the default Linux and BSD distributions. There's only 8.8 50% of the packages failing with version 3.0. And I think a lot of this has to do with turning on WError and having to deal with the more strict error reporting that Clang has. So cross-compiling with ARM and Clang. I've had to delve into a lot of the list to figure out what people have done when they're trying to figure out what triplet should work. And I started this back in about September of last year. And so the support for cross-compiling has actually improved quite a bit since then. Trying to find the right triplet seems like a magical potion. It really seems to depend on the compiler you have and the particular options that you want. The other compiler meaning the dependencies on the GNU compiler for the linker and assembler. And whether you're building the kernel or whether you're doing userspace. So the new compiler path environment variable simplified things quite a bit. Now it's much easier to specify where the compiler is. And so this is the command line that I've been using and the triplet that I specified to do userspace compilation. And it seems to work okay for our architecture. If I didn't specify the march, I found out that it's actually defaulting to ARM v4t. And if I used ARM v7 in the name of the triplet, then it couldn't find the GNU toolchain at all because it's looking for this long name as the prefix of the compiler. So there's a lot of tricky pieces to it. And you have to get everything just right for it to actually work. So whenever you look at bugs that have been filed regarding issues that come up with cross-compilation, the end result always ends up in, well, look at the universal driver. And the universal driver will address all these things, and you just will have a config file, and then you can specify everything in the config file, which I was thrilled about, and it looked great, but I can't find any information about the status of the universal driver. So if anybody can help point me at who's working on it or if it's being worked on, that would be wonderful.
Talk to James Malloy.
James Malloy?
I think he knows about it.
Okay, thank you. Another interesting project in this space is ELLCC, which is making a cross-compiler for multi-targets. So you can see there's a wide range of targeted architectures. And they have this live on a web page. So you can go there, you can paste in whatever code you want. You can set the optimization levels you want, what the source language is, what the target is that you're generating for, and compile the source code. And it will show you all of the generated assembly that was done by the compiler. And it works. It was very neat. And the fact that it actually does support all these architectures and you can use it today is one approach. So this is different than the universal driver. I have not tried using this for my compilation, but it sort of shows what's possible for state-of-the-art cross-compilation using LLVM and Clang. So now building the kernel. Definitely some challenges. There was some work done previously by Bryce Lebach for the x86 kernel. He had presented at a previous Linux Collaboration Summit meeting talking about things that he had found. There has been very little work done, I think, in the last year to 2 years on that. And so the work that I've done, I just started afresh. And I may have rediscovered some of the things that he had already found, but I definitely found some new ones because my focus was on ARM architecture and not on x86. Yeah, so one of the key problems was just getting the cross-compilation part right. And all the issues that I mentioned about getting the triplet right. There are still more issues with the triplet in the context of the kernel than user space, and I'll get to that a little later on. Warnings. The kernel uses a plethora of instances of things like memset. It calls to functions which return a value, but the value is unused. And when you have -WError on, this is a different syntax or different behavior than GCC. GCC will let that go. They don't care. It's not a problem. If you turn on WError, you don't get an instance. I get thousands of warnings when I have that turned on in the kernel. And so in order to actually find anything useful in the output, I had to generate a complete patch set for all of the things that return a value but don't actually have it used in the kernel. And I don't know if there's a way to change that or turn it off or something, but it's a stumbling point because it is a massive patch. And I don't think the patch would be accepted by the kernel community. There are some bugs that I found, more architecture-specific bugs in the back end for ARM. And there are some inline assembly bugs or differences in behavior which I haven't been able to resolve regarding the tracing functionality inside of Linux. And then there's lots of instances of scripts inside the kernel that require undefined GCC behavior, and I'll talk about some of those too. So in the scripts kbuild include directory, there's something called CCOption, and what they do is they test for the compiler's support of a particular option passed in on the command line. And so the way that GCC works is if you do that and you test it in a particular way like this, it will return false if the flag's not supported. And then so CCOption then says, well, then use this flag instead. But Clang has no notion of this. Clang will tell you when something wasn't used. And from the documentation, I can't actually know for sure if that means that it isn't supported or if it just wasn't used by that particular back end, and if there's actually a difference in that. So it will report that it wasn't used, but it won't give you an error. So when CCOption is called and you actually are using Clang, it will say, I didn't use this flag, but everything's good. So it will just accept that flag and not try to use the other one instead. So I had to create a new version of CCOption which would try to use Clang semantics to generate something similar to the result that you'd want. I would like to find somebody who can help me understand this behavior and understand the intent of it so that I make sure that I'm handling it the correct way. To the best of my knowledge, there is no notion of whether a flag is supported in Clang or not. It's just a matter of whether it's unused. There are a bunch of unsupported GCC flags. I'm not going to describe them all. They're in the slides if you'd like to see exactly what they mean. But the conserve stack, fdelete null pointer checks, and no inline functions called once. I think for the last one, there's already a bug filed in the set of bugs that are related to compiling Linux with Clang. So the kernel uses a few GCC extensions that are not supported by Clang. They're not conformant with C99. And one of them is variable length arrays and structs. And I think this came from Ada, if I remember historically why they had this. And it just happened to be supported in the compiler, so they said, hey, we can use it. When you have a struct and you're passing in a variable length array, in GCC that's completely valid. In Clang it doesn't work. There's a syntax that is supported. And there's about 3 different places inside the kernel that actually do use this. And it's not that hard to work around. And I think that based on the feedback I got last week, the kernel community would be amenable to making this change to be more supportive of LLVM and Clang. Another one's register variables, explicit register variables. So in GCC, you can say something like the above, and that will actually assign current SP to be the value of the stack pointer. It will allocate that register. In Clang, when you do this, you get the wonderful value of 0 for your stack pointer, which leads to all kinds of nice behavior. So that failed in wonderful ways that I was having to figure out, and then I finally found out that actually that returns a 0 for Clang. So I got some great feedback when I filed the bug about why this is actually not correct behavior based on the spec. But the way that it fails would be wonderful if there's a warning from Clang that could tell you, do you really mean that this should be null or this should be 0? Because it leads to some really bad behavior. Nested functions are another unsupported feature, and that I think is only used in a ThinkPad driver, and I didn't deal with it because I was dealing with ARM architecture. So yeah, the incompatibilities, I mentioned the warnings for unreturned or unused return values. One thing I did find that was different was when the code compiled fine with GCC, and then I compiled it with Clang, occasionally I would get these segment reference warnings. And so in the kernel, you have sections marked as init data or as exit data, and then they're used in other functions. And so I often had to mark them as having ref data specifically when I compiled with Clang and not with GCC. So there's some difference in the way that it's doing the section naming, and I haven't had time to investigate it yet, but that's on my to-do list. The inline syntax handling, there's a GNU 89 flag that you can use. I have not turned it on. I'm trying to get the kernel to work with the standard C99 semantics and just add the patches that are necessary. Another thing Clang had some problems on and actually crashed on was when you had inlined functions that were then passed via export module, which GCC seems to be okay with, but Clang completely crashes on. And that may be due to the difference in the GNU 89 inline versus C99 inline semantics. So another thing I came across was MABI Linux is not supported on ARM right now using Clang and LLVM. What happens is when you turn that on, it doesn't complain about it, but it doesn't use the Linux semantics. Linux generally is expected when you have an enum to allocate 4 bytes to it and not have variable length enums. That seems to work partially, but then part of LLVM actually does something different. So you end up with the offsets to your structures being one thing and where things actually are allocated to be something completely different. So when you go to access the parts of the function, you get wild values that are just not correct. That one took a long time to figure out. 64-bit type handling is broken in ARM. There's actually a patch that was made by QuIC and submitted upstream. I don't know if it's integrated right now. But if you have multiple arguments that are passed to a function, and some of those arguments are a 64-bit type, you can have them not allocated to a proper register pair in ARM. So instead of having 0 and 1 or 2 and 3, you get 1 and 2. And what happens is the value that you get then chokes because you only get half of what you're expecting. I think that was the main part of the function passing. There's also problems with inline assembly syntax and 64-bit types. GCC has, again, some undocumented features of how to allocate the upper or lower registers that are used of the register pair for that type. And there is no supported syntax in LLVM for that at all. So I had to, in MSM architecture, it uses the 64-bit types defined in atomic.h, and I just had to comment those out for now until I can have that support added. And I believe QuIC has actually a patch for that as well, which is, I think, pending review before it can be submitted upstream. The integrated assembler was not enabled by default for ARM, as I believe it's still incomplete, so I did not try that in what I have done so far. Another thing which I would appreciate your help to understand is when I am compiling user space applications, the triplet that I had before worked fine, where I had the ARM Linux GNU ABI. When I'm trying, I can't use that for the kernel because it gives me all these complaints about not having a reference to the __ a EABI functions. So if I just pass in ARM or ARM v7 as the triple when I compile the kernel, it compiles fine, but then it gives me the other warning that says my compiler does not have EABI support, which messes up the ARM unwinding stuff. So I'm not quite sure what I'm supposed to do. I'm not sure what the right behavior is and which thing I'm supposed to fix to make it be correct. Another weirdness was kernel size t. So in the Linux kernel size t is defined as an unsigned int. And in Clang, it defines the POSIX functions as unsigned long. And so every single one of these POSIX functions was complaining that the two definitions were incompatible. So I had to make a patch for that as well. So status of building the kernel. So those were some of the issues. So I set up a project at Linux Foundation for llvm.linuxfoundation.org to try to make a place where we can consolidate all the information about building the kernel. People can participate, leverage what I've done already. Jan-Simon Mollier from Linux Foundation is also here. He's been working on the project, so you can ping him too if you want. So we set up an automated build framework that just makes it easy to experiment with this. and all the dependencies are there. You should be able to just go into one of the target directories and type make test, and it will download the latest version of LLVM, the latest version of Clang, the latest version of QEMU, the latest version of the kernel, the patches for the kernel. It will apply everything. It will track which patches apply. It will keep a list of the ones that don't, and it will spawn up QEMU. It will create a compiled init.rd to run with it under QEMU. It uses Toybox, which is like a BusyBox replacement, but it's actually BSD licensed. It uses Dash, which again is BSD licensed, and then creates a basic user space, which I can test. And for Versatile Express, it actually runs. So I can type make test, and it will go and spawn up QEMU and dump me into a shell. And the whole thing was compiled with LLVM. Not the boot scripts, nothing else. No use of GCC was needed, other than just the linker and assembler. So right now I have the Versatile Express platform that's in there. Qualcomm MSM support is in there. There's no external emulator for that. So right now all I'm doing is continuous integration testing, and it's set up inside Qualcomm. So we actually pull from this repository and do continuous integration. And whenever it breaks, I fix it. The reason we're not even trying to run it yet is I've had to stub out some of that code that's not working because of the 64-bit type handling. So when that gets upstreamed and fixed, then we can actually start to debug any issues that we find with the Clang compiled version. Would definitely love to see more architecture supported. I'm just spread thin trying to do more than I am now. So if anyone who works with x86 or MIPS is interested in working with this, I'd be more than happy to help set them up and get them involved in the project. Yeah, I've mentioned that it automates all this part. The way the patches are organized, it's all hierarchical. So there's common patches, which are applicable, architecture independent in a common directory. Then there's an architecture directory, so there'd be ARM and MIPS and so forth. And under the ARM directory, it's things that apply to all ARM targets. Then within each target directory, there's the patches which apply to those. And the patches are actually broken out as required patches and patches which are only to reduce warnings. And so anybody who adds a new architecture can leverage anything that's in the hierarchy already and just has to add the extra parts. And if you don't care about the warnings part, you can just pick up the ones you need. So I'm maintaining it this way so that there's a lot of separability and visibility into which patches had to be provided. I also made a whole bunch of Python tools for managing the patches so that when I track which ones don't apply, I have scripts which can basically go and just prune all the things out of the patch set that don't apply anymore. I have some scripts that do auto patching. So based on the output that I get from Clang from the build, I can take that really nice, robust diagnostic output and generate patches for a lot of the problems like these warnings that I get for unreturned values. And so I just generate a whole new patch set. The include files so for each target, it just includes the things that it needs, like QEMU, for instance, and the init.rd. So at any point, you can just go into a target directory and type make list targets, and it will tell you any possible thing you can build. So if I do like make sync, make QEMU sync, it will just sync the latest version of QEMU. Or if I go make kernel sync, it will just sync the latest version of the kernel, and then I can do an incremental build. So the approach I took was no patches at all to Clang. All the patches are done to the Linux kernel, and generally they're done for the explicit register variables, the variable length arrays and structs, and then these linkage differences that I'm finding between Clang and GCC. Those were really the only critical things that had to be fixed to get it to compile, and the rest of it was just more or less getting rid of all the other warnings so that I could actually see some useful diagnostic output from the build. The compiler path variable made it much nicer to work with the dependent GNU tools. And as I mentioned, the output made it actually possible to do some auto-generation of patches. So I mentioned the ref data. Yeah, unused. So the last time, right before I was tied up making this presentation and then away last week, it was about 2 days before I left for the last conference that the Versatile Express platform broke. with the latest pushes to the kernel. So I haven't had a chance to debug it. So one of the things I was talking with Jan Simone about is adding git bisect support. So when this breaks, we can just do a git bisect and figure out which patch actually broke the LLVM build, and then I can try to figure out how to generate the patch and figure out whether it's something for the kernel or something with LLVM. And as I mentioned, for MSM, it doesn't build a bootable image yet, but it's still providing useful output for the continuous integration build that we have. So ARM-specific issues. The kernel uses m-little-endian. From what I understand, m-little-endian is redundant because all that Clang supports right now is little-endian. There's no thumb interworking, and the flags are there, this m load bytes, and I will show you what those are. Yeah, one of them that are explicit register variables. It's just a very simple replacement, and it's just a matter of getting the community to understand that it only takes a simple patch like that to be able to support the compiler and have both GCC and Clang supported with the same syntax. And these are the descriptions of those flags that aren't supported for ARM. So, x86 support is something I would definitely like to see. I've tried to stub in some of the initial parts that need to be there to add support. I'm going to have to go back to look at what Bryce Lebach did, because what he had reported was GCC had to be used for some of the boot code, and Clang couldn't compile it. But that was, again, about a year and a half ago, and the inline assembly support handling of Clang is much better, so I'm hoping it will just work, and I won't have to solve that problem. And there was a few other parameters which weren't supported specifically for x86. I would like to try using the integrated assembler for ARM and see how that goes. I need to dive in and figure out what's different, causing these segment linkage differences and the inline differences for the tracing part. We want to set up the Linux test project on a simulated SD card that can be used with QEMU, so that when the Clang built kernel is running, it's going to go and spawn up and actually run through the Linux test project test suite. So therefore, we can validate the generated kernel much easier. And then so I filed a few different bugs. What I would like to do is set up some a test suite for those. So when I sync the latest version of Clang, I can just run through the test suite to see if any of them have actually been fixed in the upstream, and then I can get rid of the patches that I have for those. So if this does interest anybody, if you're using Linux in your work and you would like to start to compile the kernel with Linux, I certainly welcome you to participate in the project. Adding x86 support is probably the next thing that we'll try to take on. And hopefully MIPS will be added as well in the future. So that's the status update. Yes?
Which part of the integrated assembly doesn't work? I wasn't clear what, is it the direct object containers not working, or just when you use inline assembly with that, or what? Wasn't sure what.
Yeah, so I haven't delved into the why. All I know is that it's not the default assembler for ARM. It is for x86 now, but it's not for ARM. And the reason I was given.
So iOS only, it's on by default, but for ELF targets, it's not. Yet.
Okay. And that's just because the ELF handling is not.
It's not so well tested yet.
Okay. So.
Parsing is not complete for ELF.
The which, I'm sorry?
At least assembly parsing is not complete for ELF.
Okay. All right.
I'm not sure to go directly to object what's working on for ELF.
Okay. So it's probably just that it's not very tested, and I had enough problems that I just didn't take that on yet.
You talk about the direct object, that's just to understand. The direct object from the requirement.
Yes.
Okay, okay.
Well, the integrated assembler does both inline assembly
Right.
functions.
Yes.
You mentioned some unsupported flags by Clang.
Yes.
So wondering sort of, which ones of those are unsupported, i.e. they won't work, or unsupported as in they're kind of benign, we don't care. So for example, one of the examples was no thumb interworking, which is the default anyway, because the driver doesn't accept it, but it works because that's the default. So
Okay. So all I have visibility into is what Clang's reporting, and it's reporting that these are all unused. So I'm assuming that the backends just don't check for them. So
Or the driver just doesn't pass it through to the CC1 executable, which is...
So this is the part I don't know, right? I don't understand the flow to know what it means when Clang reports that these things aren't used. Does it mean that the behavior that they normally have is actually the default and so the flag's not needed? Or does it mean that none of the backend's using it, or it got passed through to something that might have used it, but we just don't know?
It means the driver dropped it. Like the driver never looked at that flag.
Okay.
So the driver code just goes looking, oh, you have a dash L2, you have this, you have this. It means that the driver never looked at that flag. It
Does not understood it at all.
Yeah, not even consider it.
Yeah,
Like,
but you're right there, it could stem from several reasons. It could stem from it's a fix meaning you haven't implemented it yet, like for example the struct handling that you mentioned,
Yes.
the ACS Linux.
Yep.
Or it could just be, we do it anyway and it's just an unsupported GCC specific option that we just don't care about because no one really uses it type thing, but it works.
Right.
There could be several reasons for that.
It would be wonderful to have some clarity on that somehow. I don't know how best to do that, but even if I'm happy to document it here at the Linux site to say this is just not supported or this is not handled by these particular backends or what it is, but to just provide that clarity would be great. Yes?
Most of those kind of questions you can get resolved on the dev side.
On LLVM dev or?
Most of the questions you can answer.
Okay. Thank you. Yes?
Yeah, you mentioned this option for not when you dereference null.
Yes.
Should the compiler consider that to be undefined?
Well, when you go to explicitly assign a register to something which is null, that may be something you could probably guess is wrong.
No, I meant there's this option minus F, no delete null.
Oh, yes, sorry, yes. I do remember that one, yep.
Yeah. So this came up, this was added to GCC fairly recently, right? Because the Linux kernel people observed that GCC was eliminating code because it could tell that there was previously a null pointer dereferenced. No, it was eliminating null checks because the pointer was later, because the pointer was already dereferenced. But the problem is in the kernel, at least for that architecture, dereferencing null was actually perfectly valid.
Yes, I remember that, yes.
So I think it's probably quite easy to add support for this.
Okay.
And the reason is that LVM only considers dereferencing null to be invalid in the default address space. So pointer types can have different address spaces. Okay, the default address space, there null is considered special, but non-default address space, null is just not considered special. So, except for bugs, it should only be doing this for pointers in the default address space. So with this, if you have this option, Clang could simply put all pointers in some kind of fake address space it invents. It just invents, address space 250 or something.
All these special address spaces for the thread local stuff.
Yeah, exactly. So it could just, when it sees this flag, it just puts, rather than using default address space for everything, it just uses some artificial address space for everything, and then
It'll work.
optimizer will no longer be making all these assumptions about the meaning of null. So
Okay.
I think that's probably pretty easy.
Okay, great.
Yeah,
Yes.
by the way, sorry, for stack usage as well. I mean, in GCC, they did quite a bit of work to reduce the amount of stack usage. I mean, the Linux kernel, especially if you've got like just one page stack frame, if you've got a big stack usage in a function, that can really kill you because you can overflow the stack. I mean, have you seen problems with this? Because I think LVM tends to produce quite a lot of stack usage.
If no inline functions called once, I guess that's for that reason, right?
Yeah, well, I don't know. Don't actually know.
I had problems in Firefox for
Cleaning.
like you have a function that has like small stack, but in a loop calls a function a gigantic stack. So if this function recurses, now instead of recursing like have a small stack, allocate big one, go back, recurse. Now we have every recurse invocation is using
It's a huge stack, yeah.
Yeah.
I haven't come across any problems with stack dumping or anything or crashing because of that yet. And I'm running in QEMU, it's fairly constrained. The simulated environment is fairly constrained, so it seems to be okay. Yes? I'm building with default, which I believe is 02 in Linux. Yeah.
Any indication at this point that the
I've not yet moved on to performance. I'm just trying to get actually something that runs at this point. And when I can get like to the LTP time, when I actually have something that reliably comes up and can run through a test suite, then I can start baselining and doing regression testing. Great. Thank you very much.